Welcome, friends. I'm so glad you're here, whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion. You found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of an interstellar visitor, a comet that arrived from elsewhere, passed through our sun's light, and taught us something quiet about what hides beneath frozen surfaces. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The object appears first as a smudge on a digital sensor, a faint streak among 10,000 other streaks that cross the sky each night. It moves against the stars with a motion that seems, at first, unremarkable. Asteroids do this. Comets do this. The solar system is full of small bodies tracing their elliptical paths around the sun, and most of them announce themselves with exactly this kind of gentle persistence, a slow drift across the frame. A predictable arc that computers can trace backward and forward through time. But this one is different. The numbers, when they come back from the calculation, do not close into an ellipse. They open outward into a hyperbola, a trajectory that does not return. The object is moving too fast, coming from a direction that does not fit any known orbit around the sun. It arrives from interstellar space, from the region between stars where sunlight fades to nothing and objects drift in the galaxy's slow currents, unbound to any single gravitational center. The designation arrives within days. 2I/Borisov. The I stands for interstellar. The 2 inches means it is only the second object of its kind ever confirmed, only the second visitor from beyond the solar system that humanity has managed to notice and track. The first 1I/Oumuamua passed through 2 years earlier, tumbling and accelerating in ways that still provoke quiet arguments among researchers. But 2I is different from the start. It develops a coma, a soft haze of gas and dust that surrounds its nucleus like breath in cold air. It brightens as it approaches the sun. It behaves, in other words, like a comet, something familiar, something almost ordinary, except for the fact that it was not born here. Later, the object receives a second name, more personal than the catalog designation. It becomes known as Borisov, after Gennady Borisov, the amateur astronomer who first spotted it through his homemade telescope at the Margot Observatory in Crimea. He has been searching the sky for years, looking for comets and asteroids, checking the same patches of darkness over and over with patient repetition. On August 30th, 2019, his persistence catches something no one was expecting. The discovery is confirmed, and the news spreads through the network of observatories that monitor the sky. A visitor from elsewhere, close enough to study, bright enough to track. Only took 4.5 billion years for the second one to show up at a time when humans had cameras ready. Only needed the right person looking at the right patch of sky on the right night. Only required that the object pass close enough to the sun to warm up and start outgassing, making itself visible against the background dark. Telescopes turn. In Chile, in Hawaii, in Arizona, in Spain, instruments that usually divide their time among 100 different projects suddenly share a common target. The object is moving quickly through the inner solar system, and there will not be much time. It will swing around the sun, accelerate back outward, and disappear into the galaxy again, never to return. Every observation matters. Every spectrum, every image, every measurement of brightness and color adds another small detail to the understanding of what this thing is and where it came from. The first question is structural. What is it made of? Spectroscopy reveals the presence of carbon monoxide and water, molecules that sublimate from frozen ice when sunlight warms the surface. This is consistent with comets born in our own solar system, bodies that formed in the cold outer regions of the protoplanetary disk and have spent billions of years storing volatile materials in their frozen hearts. But there are differences. 2. Subtle shifts in composition. Ratios of molecules that do not quite match the average of solar comets. The visitor carries a chemistry that formed somewhere else, under conditions set by a different star. The second question is velocity. How fast, and from where? The trajectory traces back through space, pointing toward a region of the sky in the constellation Cassiopeia. But tracing an object's path backward through interstellar space is not a simple calculation. The galaxy rotates, stars move. Gravitational perturbations from nearby stellar systems nudge objects over millions of years. And the farther back the calculation goes, the wider the uncertainty becomes. The best estimates suggest the object has been traveling through space for millions of years, maybe tens of millions. Adrift in the galactic disk since it was ejected from whatever planetary system gave it birth. No one knows what that system looked like. No one knows if planets still orbit that star, or if the star itself still burns. The visitor carries no record of its origin except the chemistry frozen into its ice and the velocity imprinted by whatever gravitational interaction flung it into interstellar darkness. It is a messenger, but the message is written in a language that requires patient decoding. Isotope ratios, albedo measurements, gas production rates, subtle clues embedded in reflected sunlight. The third question is thermal. How does it respond to heat? As the object approaches the sun, it brightens. This is expected. Comets brighten as they warm. Ice sublimates, releasing gas and dust that scatter sunlight, creating the coma and sometimes a tail. But the brightness curve of 2I/Borisov does something interesting, something that will become the quiet center of this story. It does not brighten and fade in the simple pattern of surface heating. Instead, it continues to brighten even after it passes perihelion, the point of closest approach to the sun. It continues to release gas even as it begins moving outward, away from the sun's warmth, back toward the cold. This is the thermal lag, the delayed response of a subsurface that remembers heat longer than the surface does. It is the first clue that something beneath the frozen exterior is insulating the interior, slowing the transfer of energy. Storing warmth like a stone holds the heat of a fire long after the flames have gone out. Only, in this case, the stone is not dense and solid. It is porous, fragile, mostly empty space. A structure so delicate that it seems almost impossible it could survive the journey between stars. But it did survive. It arrives intact, outgasses on schedule, and begins to reveal, through this one small thermal signature, the hidden architecture of its interior, a secret written in the way heat moves through frozen voids. The measurements continue. The numbers accumulate, and somewhere in the data, a picture begins to form. Gennady Borisov builds his telescope himself, grinding mirrors, aligning optics, calibrating sensors in a process that requires months of patient adjustment. The Margot Observatory is not a research institution with rotating domes and climate-controlled instrument halls. It is a small facility in Nauchny, Crimea, where one person can still make discoveries by watching the sky with disciplined regularity. Borisov searches for near-Earth objects, asteroids, comets, anything that moves against the fixed background of stars. He photographs the same regions night after night, comparing images, looking for the subtle displacement that marks a moving body. On the night of August 30th, 2019, he finds one. The object is faint. Magnitude 18. Barely distinguishable from the background noise. But it moves. and the motion has the characteristic blur of something releasing gas, a comet, then not an asteroid. He reports the discovery to the Minor Planet Center, the clearinghouse for observations of small solar system bodies. Within hours, other observatories confirm the object's existence and begin tracking its position. The initial orbital calculations suggest something unusual. The eccentricity is high, too high for a typical comet. Follow-up observations refine the numbers, and the truth emerges. The orbit is not closed. The object is on a hyperbolic trajectory. Moving at more than 30 kilometers per second relative to the Sun, it came from interstellar space. It will return to interstellar space. The solar system is just a brief perturbation in a journey that began long ago and will continue long after the object fades from view. Only took one person looking at the right moment. Only required clear skies and functioning equipment on that particular night. Only needed the object to be bright enough, close enough, active enough to register on a detector designed for much closer targets. The astronomical community responds quickly. Observing time is rescheduled. Proposals are fast-tracked. Instruments that normally book months in advance suddenly find gaps in their schedules for this transient, time-sensitive target. The Hubble Space Telescope images the comet in October and November. The European Southern Observatory's Very Large Telescope captures high-resolution spectra. Observatories in Chile, Spain, and the United States track the object's brightness as it moves through the inner solar system. The discovery comes at a better time than Oumuamua's did. That first interstellar object was spotted only after it had already passed perihelion and was speeding away from the Sun, giving astronomers just a few weeks to gather data before it faded beyond detection. Borisov, by contrast, is discovered on approach, while it is still brightening, still moving toward perihelion. There are months to prepare, months to observe, months to collect the kind of detailed measurements that Oumuamua never allowed. The object reaches perihelion on December 8, 2019, passing within 2 astronomical units of the Sun, twice the distance from Earth to the Sun, well outside Earth's orbit, far enough to remain safe but close enough to warm significantly. At this distance, sunlight is strong enough to sublimate ice, to drive outgassing, to activate the processes that make comets visible. The coma expands. Dust grains lift from the surface, carried by escaping gas. A faint tail develops, stretching away from the Sun in the classical comet geometry dictated by radiation pressure and the solar wind. Spectroscopic observations begin to reveal composition. Water is present, as expected. Carbon monoxide appears in significant quantities, more abundant relative to water than in most solar system comets. Cyanide radicals show up in the spectra, along with diatomic carbon. These are the molecular fragments produced when ultraviolet sunlight breaks apart larger molecules frozen into the comet's ice, a chemistry that is familiar from countless observations of local comets, but with ratios that suggest formation conditions slightly different from those in our protoplanetary disk. One mystery that emerges is the isotopic composition, particularly the ratio of deuterium to hydrogen in the comet's water. This ratio varies among solar system comets depending on where they formed. Objects from the Kuiper belt have different ratios than objects from the Oort cloud, which in turn differ from the ratio found in Earth's oceans. The measurement for Borisov is difficult, requiring long exposure times and careful analysis, but preliminary results suggest a ratio within the range of solar system comets. This implies that water formation processes around other stars may not be fundamentally different from those around our own Sun, a quiet hint that planet formation might follow similar patterns across the galaxy. The color of the comet is measured photometrically, how much light it reflects at different wavelengths. Borisov appears slightly redder than the average solar system comet, consistent with organic compounds processed by cosmic rays during its long journey through interstellar space. Cosmic rays are high-energy particles that pervade the galaxy, and over millions of years, they gradually alter the chemistry of exposed surfaces, darkening them, reddening them, creating complex organic molecules from simpler precursors. The red color is a clock of sorts, though one that runs too slowly and too noisily to provide a precise age. The nucleus itself is difficult to measure directly because it is hidden within the coma, surrounded by the cloud of gas and dust it produces. Estimates based on brightness and assumptions about albedo suggest a nucleus somewhere between several hundred meters and a kilometer across, small by comet standards, fragile, ancient. If it were much larger, it would have been detected earlier. If it were much smaller, it might not have survived the journey intact. Observations continue through the autumn of 2019 as the comet approaches the Sun. Brightness measurements are made every few nights, tracking the increase in reflected light as the distance decreases and outgassing intensifies. The brightness curve follows the expected pattern at first, a steady rise as the comet warms, releasing more and more gas as the subsurface ice heats up. But there is a subtlety in the curve, a feature that will become more apparent after perihelion, when the comet begins its outward journey and the heating should, by all simple logic, begin to reverse. Only needed patience to notice, only required enough data points to see the pattern, only took observers scattered across the planet, checking the same small moving dot over and over, building the curve one measurement at a time. The media pays attention briefly. Headlines announce the interstellar visitor, the second one ever found, the first one that looks like a comet. There are comparisons to Oumuamua, speculation about extraterrestrial origins, questions about whether the object could carry microbial life frozen into its ice. Most of these questions fade when the spectroscopy confirms ordinary comet chemistry: water, carbon monoxide, cyanide, dust, nothing alien, nothing impossible. Just a comet from elsewhere, following the same physics, obeying the same thermodynamics, behaving like objects humanity has studied for centuries. But the thermal lag, when it is finally recognized, suggests something more interesting than exotic chemistry or alien biology. It suggests structure, a specific kind of internal architecture that affects how heat moves through the object, how gas escapes, how the comet responds to the sun's warmth over days and weeks. It is a clue written in brightness measurements, in the delayed peak of outgassing, in the slow fade that continues long after the surface should have cooled. Perihelion passes. The comet swings around the sun and begins its exit, accelerating outward on the hyperbolic trajectory that will carry it back into interstellar space. The distance increases, the sunlight weakens, the surface temperature should drop, and the outgassing should decline in response. This is the expected behavior, the pattern observed in thousands of comets over centuries of study. Heat the ice, it sublimates. Remove the heat, sublimation slows and stops. But 2I/Borisov does not follow the simple pattern. The brightness continues to increase even after perihelion. The gas production rate, measured by the strength of emission lines in the spectrum, does not peak at closest approach to the sun. Instead, it peaks days later, sometimes weeks later. Depending on which molecule is being measured, carbon monoxide lags behind water, dust production lags behind both. The comet is responding to heating that happened earlier, warmth that has penetrated beneath the surface and is now slowly diffusing outward, driving sublimation from ice layers that were not directly exposed to sunlight. This is the thermal lag, the time delay between heating and response, caused by the slow conduction of heat through insulating material. It is a phenomenon observed in solar system comets, particularly in those with thick dust mantles or highly porous interiors. But in Borisov, the lag is pronounced, lasting longer than expected, suggesting that the subsurface is exceptionally good at insulating, exceptionally slow at conducting heat. Researchers begin modeling the effect. They construct numerical simulations of heat diffusion through porous ice, adjusting parameters like grain size, porosity, thermal conductivity, and ice-to-dust ratio until the model output matches the observed brightness curve. The models require high porosity, very high, upward of 90% void space. The comet, according to these calculations, is mostly empty. Its structure resembles a frozen sponge, a delicate lattice of ice grains with vast gaps between them, held together by weak, cohesive forces and the vacuum cold of space. Only took the sun's heat to reveal what was hidden. Only required the warmth to penetrate deep enough to start releasing gas from layers insulated from direct radiation. Only needed observers to notice that the brightness did not behave the way simple physics would predict. The discovery is not dramatic. There are no press releases, no headlines announcing Comet defies expectations. The thermal lag is noted in research papers, discussed at conferences, incorporated into models. It is a detail, a small adjustment to the understanding of how comets work. But it is also a window into the interior of an object that formed around another star, a rare opportunity to infer subsurface structure from external behavior. The brightness measurements continue. Observers track the comet through December and into January, watching the slow decline as it moves beyond 2 astronomical units, then 3, then 4. The coma begins to fade. The gas production rate drops, but the decline is gradual, stretched out over weeks, consistent with a subsurface that is still warm, still releasing stored energy into space through sublimation. The thermal memory of perihelion persists long after the surface has cooled. One question that arises is how such a fragile structure could survive the interstellar journey. Space between stars is not empty. It contains dust grains, gas molecules, cosmic rays, and occasionally larger objects. A comet traveling at 30 kilometers per second relative to the interstellar medium would experience collisions with dust particles, impacts that could chip away at the surface or even shatter a weakly bound interior. The fact that Borisov arrives intact suggests either that the interstellar medium along its trajectory was unusually sparse, or that the object is more robust than the porosity models imply, held together by some combination of ices with higher tensile strength. Another mystery is the origin of the porosity itself. Solar system comets are thought to form by the gradual accumulation of dust and ice grains in the outer regions of the protoplanetary disk, a process that naturally produces porous structures because the grains do not pack efficiently. But the porosity observed in Borisov is at the high end of the range, suggesting either that its formation environment was particularly gentle, allowing very loose aggregation, or that subsequent processing, perhaps sublimation and recondensation cycles during close passes to its original star, increased the porosity over time. The thermal conductivity of porous ice is low. Heat moves through solid ice by conduction, the transfer of kinetic energy from molecule to molecule. But in porous ice, much of the volume is void, and voids do not conduct heat. The energy must travel through the tortuous pathways of the solid matrix, a process that is much slower than conduction through continuous material. In highly porous ice, the effective thermal conductivity can be orders of magnitude lower than in solid ice, creating the insulating effect that produces the thermal lag. Observations from the Atacama Large Millimeter Array, a radio telescope array in Chile, provide additional evidence. ALMA detects carbon monoxide emission from the comet and measures the gas production rate as a function of time. The carbon monoxide production peaks about 2 weeks after perihelion, a clear signature of subsurface outgassing delayed by thermal diffusion. Water production peaks earlier, closer to perihelion, suggesting that water ice is more abundant near the surface while carbon monoxide ice is concentrated deeper in the interior, where it takes longer for heat to penetrate. The dust-to-gas ratio is also measured, providing another constraint on the comet's composition and structure. The ratio is lower than typical for solar system comets, meaning Borisov produces more gas relative to the amount of dust it releases. This could indicate a composition richer in volatile ices, or it could reflect a structure that allows gas to escape more easily while retaining dust. Either interpretation is consistent with high porosity. Gas can diffuse through the voids, while dust particles remain trapped in the matrix until the structure weakens enough to release them. Photometric observations in different wavelength bands, ultraviolet, visible, infrared, provide information about the size distribution of dust grains in the coma. Smaller grains scatter blue light more efficiently, while larger grains are more neutral in color. The color of Borisov's coma suggests a mix of grain sizes, with a slight preference for smaller grains, consistent with fragmentation of larger aggregates as they lift off the nucleus. The presence of these small grains supports the idea of a fragile, loosely bound surface from which particles can be easily dislodged. The tail structure is also analyzed. Comets develop two types of tails: a dust tail, curved and yellowish, pushed by radiation pressure, and a gas tail, straight and bluish, swept back by the solar wind. Borisov shows both, though neither is particularly prominent. The dust tail is faint and short, suggesting that dust production is modest. The gas tail is detectable in ultraviolet images, indicating active outgassing, but not at the intense levels seen in some solar system comets during close perihelion passages. One small irony noted by researchers is that the first interstellar object looked nothing like a comet, while the second one looks exactly like a comet. Oumuamua was elongated, non-outgassing, tumbling, and possibly covered in an organic crust. Borisov is round, active, stable in rotation, and compositionally familiar. The two objects suggest that interstellar space contains a diversity of bodies, just as the solar system does, some rocky, some icy, some in between, each carrying the signature of its formation environment and its subsequent history. The thermal lag, in this context, becomes one more piece of evidence that comets elsewhere form through processes similar to those in our own system. The porosity is not exotic. The thermal behavior is not alien. It is simply the natural consequence of ice grains accumulating slowly in a cold environment, building a structure full of empty space, and then being ejected into the galaxy where time and distance erase all memory of origin except what is frozen into the ice itself. The concept of thermal lag is not new to cometary science. Observers have noted delayed brightness peaks in solar system comets for decades, recognizing that the subsurface does not respond instantly to changes in solar heating. The surface warms quickly when exposed to sunlight, but heat takes time to penetrate deeper layers. This time delay depends on several factors: the thermal conductivity of the material, the porosity of the structure, the distance from the sun, and the rotation rate of the nucleus. For a solid, non-porous object, heat diffuses inward at a rate determined by the material's thermal diffusivity, a measure of how quickly temperature changes propagate through a substance. Ice has a relatively low thermal diffusivity compared to rock or metal, but it is not negligible. In solid ice, heat from the surface can penetrate several centimeters in a matter of hours, enough to drive sublimation from subsurface layers during a single day-night cycle on a rotating comet. But in porous ice, the situation is different. The voids interrupt the conductive pathways, forcing heat to travel through a much smaller cross-sectional area of solid material. The effective thermal diffusivity drops by a factor that depends on the porosity. The higher the porosity, the slower the heat penetration. In ice with 90% porosity, heat might take days or weeks to penetrate the same distance that solid ice would conduct in hours. This creates a thermal gradient within the comet. The surface heats up during the day and cools at night, but a few centimeters down. The temperature changes are muted, smoothed out by the insulating effect of the porous structure. Deeper still, the temperature lags even further behind, responding to the average heating over many rotation periods rather than the instantaneous solar flux. And deep in the interior, tens of centimeters or meters below the surface, the temperature may remain nearly constant, changing only on the timescale of the comet's orbital period, or, in the case of an interstellar object, on the timescale of its passage through the inner solar system. Only took billions of frozen grains, leaving gaps between them, only required that the structure never collapsed, never compacted, never experienced forces strong enough to squeeze the voids away, only needed the object to remain cold and undisturbed for millions of years, preserving the fragile architecture imprinted during formation. The thermal lag observed in Borisov tells researchers something specific. The subsurface is warm enough for long enough to drive significant outgassing even after perihelion. This implies that heat has penetrated to depths where volatile ices are stored, and that those ices are sublimating in response to warmth that arrived days or weeks earlier. The delayed peak in carbon monoxide production, for example, suggests that CO ice is located deeper than water ice, requiring more time for heat to reach it. One hypothesis is that the comet's interior is compositionally stratified, with different ices concentrated at different depths. Water ice, being less volatile, might be more evenly distributed. Carbon monoxide ice, which sublimates at lower temperatures, might be concentrated deeper in the interior where it can remain stable even as the outer layers warm. When heat finally reaches these deeper layers, the CO ice sublimates rapidly, producing the observed burst of gas production that peaks after perihelion. Another hypothesis is that the porosity itself varies with depth. The surface, exposed to micrometeorite impacts and cosmic ray processing during the interstellar journey, might be more compacted or armored with a crust of less volatile material. Below this crust, the original high porosity structure could be preserved, allowing gas to escape through the porous matrix while the surface crust slows the escape just enough to create the observed lag. Modeling these scenarios requires numerical simulations that solve the heat diffusion equation in one or more dimensions, accounting for the sublimation of ice, the flow of gas through porous media, and the rotation of the nucleus. The models include parameters for thermal conductivity, porosity, ice composition, and dust-to-ice ratio, and the researchers adjust these parameters until the simulated brightness curve matches the observations. The best fit models consistently point to high porosity, around 90 to 95% void space, as the key factor explaining the thermal lag. The timescale of the lag provides additional constraints. If the delay between perihelion and peak brightness is several days, heat must be penetrating to depths of several centimeters. If the delay is weeks, the characteristic depth increases to tens of centimeters or more. These depth estimates, combined with assumptions about the temperature required to sublimate different ices, allow researchers to infer the vertical distribution of volatile materials within the nucleus. One small mystery is whether the thermal lag is symmetric, whether the heating phase before perihelion mirrors the cooling phase after perihelion. If the subsurface structure is uniform, the lag should be symmetric. But if there are asymmetries, regions of higher or lower porosity, variations in ice composition, or structural features like cracks or voids, the heating and cooling curves might differ. The observations of Borisov show a slight asymmetry, with the post-perihelion decline being somewhat slower than the pre-perihelion rise, hinting at structural complexity that the simplest models do not capture. The rotation of the nucleus also affects the thermal lag. If the comet rotates rapidly, each point on the surface experiences short periods of heating followed by short periods of cooling, and the subsurface temperature averages out over many rotation periods, if the rotation is slow, or if the comet is not rotating at all. One hemisphere could remain in sunlight for extended periods, allowing heat to penetrate more deeply before the surface cools. Observations of Borisov suggest a rotation period of several hours, typical for small comets, meaning the thermal lag is dominated by the slow heat diffusion rather than by rotational effects. The gas that escapes from the subsurface must travel through the porous matrix to reach the surface. This journey is not instantaneous. Gas molecules diffuse through the voids, colliding with ice grains, bouncing from one void to the next, gradually working their way outward. The diffusion process adds another delay, separate from the thermal diffusion delay, though the two are coupled because the gas production rate depends on the temperature at each depth. The combination of thermal lag and gas diffusion lag creates the observed delay between heating and brightness increase. One irony noted in the literature is that thermal lag makes interstellar comets easier to study in some ways. The extended outgassing period means there is more time to collect data, more opportunities to observe the object before it fades. Without the thermal lag, Borisov would have brightened sharply at perihelion and faded quickly afterward, giving observers only a narrow window. Instead, the lag stretches the active phase over weeks, allowing detailed spectroscopy and photometry long after the closest approach to the Sun. The thermal conductivity of porous ice has been measured in laboratory experiments, where samples are prepared with controlled porosity and subjected to temperature gradients. These experiments confirm that thermal conductivity decreases sharply with increasing porosity, dropping by more than an order of magnitude as porosity approaches 90%. The lab measurements provide the baseline values used in the comet models, though the exact conditions in a comet nucleus, vacuum environment, mixed ice-dust composition, potential sintering or compaction over time may differ from laboratory conditions. Heat in porous ice travels not only by conduction through the solid matrix, but also by radiation across the voids. At very low temperatures, radiative transfer is negligible. But as temperatures increase, thermal radiation becomes more important, potentially increasing the effective thermal conductivity. Models of Borisov include radiative transfer, though the contribution is small compared to conduction for the temperatures and void sizes typical of comets. The slow thermal response means that the comet is not in equilibrium with its environment during the perihelion passage. The surface temperature lags behind the equilibrium temperature, determined by the balance between absorbed sunlight and emitted thermal radiation. The subsurface lags even further. The entire thermal structure is a snapshot of past heating, a memory written in the temperature profile that persists until the object moves far enough from the Sun that sublimation ceases and the interior begins to cool toward the ambient temperature of interstellar space. The porosity of 2I/Borisov is not directly measurable. There is no way to drill into the comet, to extract a core sample, to examine the interior structure under a microscope. What researchers have instead are indirect measurements, brightness curves, gas production rates, thermal models, and from these they infer the properties of the unseen interior. The inference requires assumptions, educated guesses about the composition, the ice-to-dust ratio, the albedo, the shape of the nucleus, but the assumptions can be tested for consistency, and when multiple independent lines of evidence point to the same conclusion, confidence grows. The porosity estimate of 90 to 95% emerges from thermal modeling. Researchers simulate heat diffusion through a comet nucleus with varying porosity, calculate the resulting brightness curve, and compare it to the observations. Low porosity produces a brightness curve that peaks at perihelion and declines quickly afterward, not what is observed. High porosity produces a delayed peak and a slow decline, much closer to the data. The best match occurs when porosity is pushed to the high end of the plausible range, into territory where the nucleus is more void than solid. This structure is fragile by any standard. A substance that is 95% empty space has very little solid material to hold it together. The ice grains touch each other at only a few points of contact, and the forces binding them, van der Waals forces, sintering, electrostatic attraction, are weak. A gentle push could disrupt the structure. A modest impact could shatter it. The fact that Borisov survives the journey through interstellar space, survives the tidal forces during perihelion passage, survives the outgassing that must create internal stresses as gas escapes through narrow channels, all of this suggests that the structure, though fragile, is not as fragile as it seems, or that the comet's journey has been remarkably gentle, only needed the grains to touch lightly and stay touching, only required that no shockwave, no collision, no gravitational encounter disturb the delicate balance, only took millions of years of nothing happening to preserve what formed in the first moments. The architecture of high-porosity ice has been studied in laboratory settings, where researchers create analogues by freezing water vapor onto cold substrates or by compacting ice grains under controlled conditions. The resulting structures resemble the models proposed for comets, networks of connected grains with large voids, frost-like textures, mechanical properties that are much weaker than solid ice. These analogues confirm that high-porosity ice can exist and can be stable under vacuum conditions, but they also reveal how easily such structures can collapse when subjected to even modest mechanical stress. One challenge in understanding cometary porosity is that the structure may not be uniform throughout the nucleus. The surface, exposed to thermal cycling, micrometeorite impacts, and cosmic ray bombardment, might be denser than the interior. Sublimation near the surface can remove ice, leaving behind a lag deposit of dust and larger grains that partially fills the voids, reducing porosity in the outer layers. Below this modified surface, the original porous structure might be preserved unchanged, creating a stratified nucleus with depth-dependent properties. Another possibility is that the porosity varies laterally, with some regions of the nucleus being more porous than others due to local variations in composition or formation history. Such heterogeneity could produce asymmetries in the outgassing pattern, with some regions releasing more gas than others, creating jets or active areas that dominate the coma production. Observations of Borisov do not show strong evidence for jets, suggesting that the activity is relatively uniform, but subtle variations could still exist below the detection threshold. The void space in porous ice is not empty in the strictest sense. It contains gas molecules that have sublimated from the ice grains and are diffusing outward toward the surface. At depths where the temperature is high enough for sublimation, the voids may have significant gas pressure, enough to create a flow of gas through the porous matrix. This flow can transport heat by advection, the physical movement of gas carrying energy with it, in addition to the conductive heat transfer through the solid matrix. In some thermal models, gas advection contributes to the effective thermal conductivity, slightly reducing the thermal lag compared to a model that includes only conduction. The mechanical strength of high-porosity ice is low, but it is not zero. Ice grains can sinter together over time, forming bonds where they touch, increasing the strength of the matrix. Sintering is a thermally activated process, more rapid at higher temperatures, and it can occur even at the low temperatures characteristic of comet interiors if given enough time. Over millions of years, a porous structure might sinter enough to develop modest tensile strength, allowing it to resist fragmentation during outgassing or tidal stress. The density of the nucleus can be estimated from the porosity if the composition is known. Ice has a density of about 0.9 grams per cubic centimeter. If the nucleus is 95% void, the bulk density would be only about 0.05 grams per cubic centimeter, lighter than styrofoam, lighter than aerogel. among the least dense solid objects in the solar system. Such low density is difficult to reconcile with gravitational measurements, which require a more massive nucleus to produce detectable perturbations in the trajectories of nearby objects or spacecraft. But Borisov has no spacecraft nearby, no close encounters with planets, no opportunities for precise mass measurement. The density remains an inference, a calculated consequence of the porosity model. One mystery is how such a porous object forms in the first place. Planetary formation models suggest that comets grow by accretion in the outer protoplanetary disk, where temperatures are low enough for volatile ices to condense. Small grains collide and stick, building up larger aggregates over time. If the collisions are gentle, the grains do not compact, and the resulting aggregate retains high porosity. If the collisions are energetic, the structure compacts and the porosity decreases. The high porosity of Borisov suggests that its formation involved very gentle accretion, perhaps in a low-density region of its protoplanetary disk where collision velocities were minimal. Alternatively, the porosity might have been modified after formation. Thermal cycling, repeated heating and cooling as the comet orbited its parent star, could drive sublimation and recondensation, creating a more porous structure over time. Each thermal cycle removes ice from warmer regions and deposits it in cooler regions, potentially creating voids and increasing porosity. But thermal cycling also tends to sinter ice grains together, which would decrease porosity. The balance between these competing effects depends on the details of the thermal history, which are unknown. The fact that Borisov's porosity is similar to that inferred for some solar system, Comet suggests that the formation processes are not fundamentally different. This is reassuring in a way. It implies that the physics of planet formation, the chemistry of ice condensation, the mechanics of grain aggregation are not unique to our solar system. Other stars have protoplanetary disks. Other disks produce comets, and at least some of those comets are porous, fragile, and capable of surviving ejection into interstellar space. The thermal lag, then, is not just a curiosity, it is a diagnostic tool, a way of probing the interior of an object that cannot be visited, cannot be sampled, cannot be examined except through the light it scatters and the gas it releases. The lag encodes information about structure, about composition, about the thermal history of an object that has traveled farther than any spacecraft humans have built. And that information, extracted from brightness measurements and spectroscopic observations, tells a story of fragility preserved across unimaginable distances. Heat diffuses into the nucleus of 2I/Borisov as the comet approaches the Sun. The process begins slowly, limited by the low thermal conductivity of porous ice. Sunlight warms the surface, raising the temperature to values that depend on the balance between absorbed solar radiation and emitted thermal infrared radiation. At 2 astronomical units from the Sun, the equilibrium temperature for a dark, non-rotating surface would be around 200 Kelvin, cold enough that water ice remains stable, but warm enough that more volatile ices like carbon monoxide begin to sublimate. The surface does not reach equilibrium instantly. It takes time for the temperature to rise, time for the absorbed energy to be distributed through the surface layers. And as the surface warms, heat begins to conduct inward, penetrating deeper into the nucleus at a rate determined by the thermal diffusivity of the porous ice. After 1 day of heating, the warmth has penetrated perhaps a centimeter. After 1 week, several centimeters. After 1 month, tens of centimeters. The penetration depth grows with the square root of time, a characteristic of diffusive processes, slower than linear but faster than logarithmic. As heat reaches deeper ice layers, sublimation begins at those depths. Water molecules break free from the ice lattice, enter the gas phase, and begin diffusing through the porous matrix toward the surface. The gas carries energy with it. the latent heat of sublimation, which slightly alters the temperature profile, creating a cooling effect at the depth where sublimation is occurring and a warming effect near the surface where the gas recondenses or escapes into space. This coupling between heat transfer and mass transfer complicates the thermal modeling, requiring simultaneous solution of the heat equation and the gas diffusion equation. Only needed time and warmth to wake the interior. Only required that the sun's light touch the surface long enough for the warmth to sink in. Only took the slow conduction through frozen grains to carry energy into layers that had been cold and dormant for millions of years. The temperature profile within the nucleus is not uniform. Near the surface, the temperature varies with the day-night cycle, warming when sunlight strikes and cooling during the night or when the surface rotates into shadow, a few centimeters down. These variations are smoothed out, and the temperature reflects the average heating over many rotation periods. Deeper still, the temperature is nearly constant on short time scales, changing only as the comet's distance from the sun changes, and in the deep interior, meters below the surface, the temperature may remain close to the ambient temperature of interstellar space, a few tens of Kelvin, barely affected by the brief passage through the inner solar system. The thermal wave, the propagation of warmth into the nucleus, travels slowly. It is not a wave in the mechanical sense, not a disturbance that propagates at a fixed speed. It is a diffusive process, a gradual spreading of energy governed by the diffusion equation. The characteristic depth to which heat penetrates depends on the thermal diffusivity and the time available. For Borisov, passing through the inner solar system over a period of several months, the characteristic depth is estimated to be tens of centimeters, perhaps approaching a meter in the most favorable conditions. This depth scale is significant because it determines which parts of the nucleus contribute to outgassing during the perihelion passage. Only the heated layers produce gas. Deeper ice remains frozen, untouched by the sun's warmth, contributing nothing to the brightness or the coma. The active layer is a shell, not the entire nucleus, a thin zone where conditions are right for sublimation, surrounded by cold, inactive ice. The gas produced at depth must escape through the overlying layers, in porous ice. This escape occurs by diffusion through the interconnected voids. The gas molecules move randomly, colliding with ice grains, bouncing from one void to the next, gradually working their way toward the surface. The diffusion process is relatively fast in high porosity material because the path is not obstructed by dense solid material. Gas can flow freely through the voids, creating a pressure gradient that drives the flow. But the flow is not instantaneous. It takes time for gas produced at depth to reach the surface and contribute to the coma. This gas diffusion lag adds to the thermal diffusion lag, creating an even longer delay between heating and brightness increase. The two lags are coupled because the gas production rate depends on temperature, which in turn depends on how much heat has diffused to each depth. The result is a complex, time-dependent system in which the observed brightness at any moment reflects the integrated effect of heating, sublimation, and gas transport over preceding days or weeks. Observations of carbon monoxide production provide a clear example. CO ice sublimates at lower temperatures than water ice, meaning it can be released from deeper, colder layers. When heat finally penetrates to the depth where CO ice is stored, the sublimation rate increases rapidly. But the gas must then diffuse outward through the porous matrix, a journey that takes additional time. The result is a CO production curve that peaks well after perihelion, sometimes 2 weeks or more, consistent with gas being released from depths of tens of centimeters and taking days to reach the surface. Water production, by contrast, peaks closer to perihelion. Water ice is more abundant near the surface, and it sublimates at higher temperatures. The thermal lag is shorter because the heat does not need to penetrate as deeply, and the gas diffusion lag is shorter because the gas has less distance to travel. The difference in timing between water and CO production provides a way to map the vertical distribution of ices within the nucleus, a kind of depth profiling based on thermal response. One subtle effect is that sublimation consumes energy. When ice turns to gas, it absorbs the latent heat of sublimation, cooling the surrounding material. This cooling effect can slow the inward propagation of the thermal wave, creating a feedback loop where sublimation limits further warming. In models of cometary thermal structure, this effect is included by adding a sink term to the heat equation, proportional to the sublimation rate. The result is a temperature profile that does not penetrate as deeply as it would in inert material, and a sublimation zone that remains closer to the surface. The rotation of the nucleus modulates the surface temperature, but the effect averages out at depth. If the rotation period is several hours, each point on the surface experiences roughly equal amounts of heating and cooling over the course of a rotation. The average temperature, integrated over one rotation period, depends on the comet's distance from the Sun and the surface albedo, but not strongly on the rotation rate. This average temperature determines how deeply the thermal wave penetrates over longer time scales, days, weeks, months. One mystery is whether the thermal structure persists after the comet leaves the inner solar system. As Borisov moves beyond several astronomical units, the surface cools rapidly, approaching the equilibrium temperature for deep space, but the subsurface retains warmth, stored in the thermal mass of the ice. This stored warmth continues to drive sublimation for a time, slowly leaking out through the surface as the temperature gradient drives heat outward. The thermal memory of perihelion fades gradually, over weeks or months, until the entire nucleus returns to the cold, dormant state that characterized it before the encounter. The time scale for cooling depends on the same factors that govern heating: thermal diffusivity, porosity, depth. A highly porous nucleus cools slowly because the low thermal conductivity inhibits heat loss just as it inhibited heat gain. The comet carries the sun's warmth with it as it exits, a thermal echo that persists long after the direct heating has ceased. This echo is visible in the continued outgassing, the slow decline in brightness, the gradual fading of the coma. Laboratory studies of heat diffusion in porous ice provide some context for these processes. Researchers create porous ice samples in vacuum chambers, subject them to controlled heating, and measure the temperature response with embedded sensors. The experiments confirm that heat penetrates slowly, that sublimation creates cooling effects, that the thermal response is delayed and spread out over time, but laboratory samples are small, centimeters in size, and the boundary conditions are different from those in a comet. Scaling the results to the size and environment of a comet nucleus requires careful extrapolation and validation against observations. The thermal inertia, a measure of how much energy a material can store and how quickly it responds to temperature changes, is low for porous ice. Low thermal inertia means the surface temperature swings widely between day and night, but it also means the subsurface is well insulated from these swings. This insulation is what creates the thermal lag. If comets had high thermal inertia, like solid rock, the subsurface would heat and cool in step with the surface, and there would be no delayed response. The fragility of the structure, the vast empty spaces between ice grains, is what allows the thermal lag to exist. One irony is that the thermal lag makes the comet look more active than it would be otherwise. Without the lag, Borisov would release most of its gas during the brief perihelion passage, producing a sharp brightness peak that would be missed by observers if their timing were unlucky. With the lag, the outgassing is spread over a longer period, creating a sustained display that gives observers ample opportunity to collect data. The delay is inconvenient for models that assume instantaneous thermal response, but convenient for telescopes that need time to schedule observations and accumulate signal. The heat that penetrates deep into Borisov's nucleus may never fully escape. Some of it is lost through sublimation, carrying energy away in the form of gas molecules. Some of it radiates from the surface as infrared photons, but some of it may remain trapped in the deep interior, slowly diffusing outwards over years or decades, long after the comet has faded from view and returned to the cold of interstellar space. This residual warmth is a memory of the sun, a trace of the brief encounter preserved in the thermal state of ice grains billions of kilometers away. The mathematics of heat diffusion are well understood, partial differential equations that describe how temperature evolves in space and time. But applying these equations to a comet requires knowing the material properties, the boundary conditions, the initial state. Researchers estimate these inputs from observations and from theoretical models of comet formation, but uncertainties remain. The thermal lag constrains some of these unknowns, particularly the porosity and thermal conductivity. By demanding that the model output match the observed brightness curve, it is an inverse problem, inferring the interior from the exterior, deducing the unseen from the visible. The first interstellar object, 1I/Oumuamua, looked nothing like 2I/Borisov, where Borisov developed a coma and tail. Oumuamua remained point-like, showing no signs of outgassing detectable in any observation, where Borisov followed a trajectory explained entirely by gravity. Oumuamua exhibited a small, non-gravitational acceleration, as if something were pushing it. Where Borisov appeared round and typical in shape, Oumuamua was elongated, with an axis ratio that suggested a cigar or pancake geometry. The two objects, both interstellar, both passing through the inner solar system within 2 years of each other, seem to represent entirely different categories of small body. The contrast is striking. Oumuamua arrived first, in 2017, and its strangeness provoked speculation that ranged from scientifically grounded to wildly imaginative. Was it a fragment of a disrupted planet? A chunk of solid hydrogen? A light sail built by an alien civilization? The absence of outgassing ruled out the simplest explanation, that it was a comet, and left researchers searching for alternatives. The non-gravitational acceleration, small but measurable, suggested that something was pushing the object, but without visible outgassing. The mechanism remained unclear. Borisov, arriving in 2019, brought relief in its familiarity. It behaved exactly as a comet should. It brightened as it approached the sun. It developed a coma. It released gas and dust in proportions consistent with sublimating ice. Its spectrum showed molecules found in countless solar system comets. Its trajectory was purely gravitational, requiring no exotic forces to explain. It was, in short, ordinary, except for the fact that it came from interstellar space. Only took 2 visitors to show that interstellar objects are diverse. Only required one mystery, followed by one familiar example, to reveal that the space between stars contains the same variety of bodies that orbit our sun. Only needed 2 data points to suggest that a larger population exists, invisible, passing through undetected. The comparison between the 2 objects reveals something about the population of interstellar travelers. If all such objects were like Oumuamua, non-outgassing, possibly rocky, certainly unusual, then comets might be rare in interstellar space, ejected less frequently or disrupted more easily during their journeys. If all such objects were like Borisov, icy, active, structurally fragile, then rocky objects might be the rare ones, requiring special conditions for ejection and survival. The fact that the first 2 detected objects are so different suggests that both types exist, and perhaps many others, each representing a different outcome of planet formation and ejection dynamics, the thermal lag observed in Borisov provides a point of comparison. If Oumuamua had a porous interior, would it have shown a similar delayed response to solar heating? The absence of detectable outgassing suggests either that Oumuamua lacked volatile ices, or that any outgassing was hidden beneath a non-volatile crust, or that the object was too small, too distant, or oriented in a way that made the outgassing difficult to detect. Some researchers have proposed that Oumuamua did outgasse, just barely, and that this weak outgassing produced the observed non-gravitational acceleration without creating a visible coma. If true, this would imply a porous interior similar to Borisov's, but with a composition dominated by less abundant volatiles like nitrogen or carbon monoxide rather than water. One hypothesis for Oumuamua's shape is that it is a fragment of a larger body, broken apart by tidal forces during a close encounter with a star or planet. Fragmentation could produce elongated shards, and if the parent body was porous, the fragments might retain high porosity. But fragmentation typically exposes fresh interior surfaces, which should be rich in volatiles and prone to outgassing when heated. The lack of visible outgassing argues against this scenario, unless the fragmentation occurred so long ago that the exposed surfaces were thoroughly processed by cosmic rays, converting volatile ices into a stable, non-volatile crust. Another hypothesis is that Oumuamua is a cosmic iceberg, a chunk of solid nitrogen ice, analogous to the surface ice of Pluto. Nitrogen ice sublimates readily, and the sublimation could produce the non-gravitational acceleration without generating visible dust, explaining the absence of a coma. Thermal models of nitrogen ice objects passing through the inner solar system show that sublimation peaks near perihelion and declines rapidly afterward, consistent with the observed behavior. But nitrogen ice is not stable in interstellar space over long timescales. It sublimates even in the cold of interstellar radiation fields. For a nitrogen iceberg to survive the journey, it would need to be large or young, neither of which fits well with the estimated size and age of Oumuamua. Borisov, by contrast, fits comfortably into existing frameworks. Its composition, water, carbon monoxide, cyanide, dust, is typical of comets formed in cold regions of protoplanetary disks. Its structure, highly porous, loosely bound, is consistent with gentle accretion in low-density environments. Its behavior, outgassing in response to solar heating, developing a coma and tail, follows the well-established physics of cometary activity. The only unusual thing about Borisov is its origin. Everything else is familiar. The thermal lag, then, becomes a diagnostic that distinguishes between objects with different internal structures. Borisov has high porosity and shows thermal lag. If Oumuamua has high porosity, it might show thermal lag too, but the lag would be hidden in the absence of strong outgassing. If Oumuamua is solid or low porosity, it would show no thermal lag, and any outgassing would respond immediately to solar heating. The observations do not provide enough information to decide between these scenarios, leaving Oumuamua's structure as one of its many mysteries. One small irony is that Borisov, the easier object to understand, arrived second. If the order had been reversed, if Borisov had been detected first and Oumuamua second, the narrative would have been different. Astronomers would have seen a familiar comet from interstellar space, concluded that interstellar objects are much like solar system objects, and then been surprised by the strange, non-outgassing visitor that followed. Instead, the narrative began with mystery and proceeded to familiarity, a sequence that perhaps overemphasized how unusual interstellar objects might be. The detection of both objects depended on timing and luck. Interstellar objects move quickly through the inner solar system, spending only weeks or months within detection range of Earth-based telescopes. If the object is faint, if the weather is poor, if no one happens to be looking at the right part of the sky, it will pass unnoticed. The fact that 2 were detected within 2 years suggests that such objects are relatively common, passing through the inner solar system perhaps once per year or more, but most pass undetected, too faint, too fast, or too far from the sun to be noticed. The thermal lag of Borisov is unlikely to have been observed in Oumuamua even if it existed, because Oumuamua was discovered after perihelion, during its exit from the inner solar system. By the time observers were tracking it, any thermal lag would already have been underway, and the absence of long-term brightness monitoring meant there was no way to detect the delayed response. Borisov, discovered before perihelion, offered the opportunity to track the entire brightness curve from approach through perihelion to exit, capturing the thermal lag in full. The 2 objects together provide a more complete picture of the interstellar population than either one alone. They suggest diversity, rocky and icy, dense and porous, active and dormant. They hint at the variety of planet formation outcomes across the galaxy, the different ways that small bodies can be ejected into interstellar space, the range of conditions under which they survive the journey, and they demonstrate that Earth-based telescopes, with sufficient vigilance, can detect and study these rare visitors, learning something about planetary systems beyond our own from the travelers that pass through. Porosity. 90 to 95% means that for every cubic centimeter of volume, only 5 to 10% is solid ice or dust. The remaining 90 to 95% is void, empty space, vacuum, or at most, a trace of gas molecules diffusing through. This is an extreme level of porosity, at the edge of what solid structures can achieve. Aerogels, the least dense solids manufactured on Earth, reach porosities around 99%. But they are engineered materials with carefully controlled microstructures. Natural materials rarely achieve such low densities without collapsing under their own weight. In the microgravity environment of space, weight is not a concern. A comet nucleus does not need to support itself against gravitational compression. The internal forces that hold the structure together are weak, cohesive forces between ice grains, van der Waals interactions, sintering bonds, electrostatic adhesion. These forces are sufficient to maintain the structure as long as external stresses are small. The self-gravity of a kilometer-sized comet is negligible, producing accelerations measured in microgravities. Tidal forces during perihelion passage are similarly weak for an object that does not approach closely to the Sun. The structure can remain intact because nothing significant tries to disrupt it, but the structure is fragile. A collision with another object, even a small one, could shatter the porous matrix. The impact energy would propagate through the weak lattice of ice grains, breaking bonds, creating fractures, potentially disrupting the entire nucleus. For Borisov to survive its journey through interstellar space with its high porosity structure intact suggests that it experienced no significant collisions, or that the collisions were gentle enough not to cause catastrophic damage, only needed to avoid every large obstacle for millions of years, only required that the interstellar medium along its path was sparse enough, empty enough, forgiving enough, only took extraordinary luck, or perhaps an ordinary trajectory through ordinary space where nothing much happens. The density of the interstellar medium varies with location. In the diffuse regions between star-forming clouds, the density is around 1 atom per cubic centimeter, mostly hydrogen, with traces of helium and heavier elements. At a relative velocity of 30 kilometers per second, a comet traveling through such a medium would collide with roughly 30 atoms per second per square centimeter of surface area. Each collision deposits a tiny amount of energy, eroding the surface atom by atom, over millions of years. This sputtering removes a layer perhaps millimeters thick, noticeable, but not enough to destroy a kilometer-sized object. Larger particles are rarer. Dust grains microns in size are scattered through interstellar space at densities of perhaps 1 grain per cubic kilometer. Collisions with dust grains are energetic enough to chip away small fragments of the surface, creating micrometeorite craters, but the flux is low, and most collisions occur on the forward-facing hemisphere, leaving the rest of the nucleus relatively unscathed. Over the journey, the comet might accumulate hundreds or thousands of dust impacts, eroding the surface, compacting the outermost layers, but leaving the deep interior undisturbed. Rocky fragments centimeters or larger are extremely rare in interstellar space. A collision with such an object could be catastrophic, shattering the porous structure, breaking the nucleus into smaller pieces. The probability of such a collision during a million-year journey is low, but not zero. Borisov's intact arrival suggests either that no such collision occurred, or that the nucleus has some resilience that allows it to absorb impacts without complete disruption. Perhaps the porous structure acts as a cushion, absorbing impact energy through compression of the voids rather than fracturing the solid material. Another threat to high-porosity structures is thermal stress. As Borisov approaches the Sun and heats up, the outer layers warm faster than the interior, creating thermal gradients. These gradients induce mechanical stresses. The warm material expands while the cold material does not, creating tension at the boundary. If the stresses exceed the strength of the porous matrix, fractures form. For highly porous ice, the tensile strength is low, perhaps a few kilopascals, much weaker than solid ice. Yet Borisov shows no sign of fragmentation or disruption during perihelion passage, suggesting that the thermal stresses remain below the failure threshold. The gas pressure created by sublimation also generates stress. When ice sublimates at depth, the gas must escape through the overlying porous layers. If the permeability is low, pressure builds up, creating forces that push outward on the matrix. High porosity implies high permeability. The voids are interconnected, allowing gas to flow freely. This free flow prevents pressure buildup, keeping the stresses low. In essence, the high porosity that creates the thermal lag also prevents the thermal and mechanical stresses that would otherwise disrupt the structure. One mystery is whether the porosity is isotropic or whether it has preferred directions. If the ice grains are created with random orientations, the porosity should be isotropic, the same in all directions. But if there was a preferred direction during formation, perhaps due to settling in the protoplanetary disk or compression from one side, the voids might be elongated or aligned, creating anisotropic porosity. Anisotropic structures conduct heat differently in different directions, potentially creating asymmetries in the thermal lag that could be detected in the brightness curve if the data were precise enough. The spectrum of void sizes is another unknown. Pores could be uniform, all roughly the same size, or they could span a wide range from microscopic voids between individual ice molecules to macroscopic cavities centimeters across. The size distribution affects gas diffusion, thermal conductivity, and mechanical strength. Smaller voids impede gas flow and slow heat transfer. Larger voids allow faster diffusion but reduce the number of solid connections holding the structure together. The models of Borisov's thermal lag assume a characteristic pore size based on the ice grain size, typically microns to millimeters. But the true distribution is unknown. Laboratory analogues of cometary ice suggest that porosity is hierarchical, with voids at multiple scales. Individual ice grains are tens of microns across and packed together with micron-scale voids between them. These grains aggregate into clusters millimeters across, with larger voids between clusters. The clusters aggregate into still larger structures, creating a nested hierarchy of voids. This hierarchical porosity is difficult to model mathematically, but it may be important for understanding gas diffusion and thermal transport in real comets. One irony is that the very property that makes Borisov interesting, its high porosity, also makes it difficult to study. Porous structures have low density, which means low mass, which means weak gravitational influence on nearby objects. There is no way to measure the mass of Borisov directly without a spacecraft flyby or orbital insertion, and no such mission is feasible for an object discovered only months before perihelion and leaving the solar system on a hyperbolic trajectory. The mass must be inferred from size and density must be inferred from porosity, and porosity must be inferred from thermal modeling. Each step introduces uncertainty, and the uncertainties compound. The porosity also affects how light scatters from the nucleus. A solid, smooth surface reflects light according to well-understood laws of optics. A porous surface has complex microstructure that scatters light in all directions, creating a different reflectance pattern. Observations of Borisov's brightness at different viewing angles provide some information about surface roughness and porosity, but disentangling the two effects is difficult. A surface that looks rough might actually be smooth but highly porous, or vice versa. The thermal inertia derived from the brightness curve is consistent with high porosity, but it is not a unique measurement. Other combinations of thermal conductivity, density, and heat capacity could produce the same thermal inertia. The thermal lag breaks some of this degeneracy by constraining the thermal diffusivity, the ratio of conductivity to heat capacity and density. But ambiguities remain. Different models with different assumptions about composition and structure can fit the observations equally well, leaving open the question of which model is correct. One approach to resolving these ambiguities is to compare Borisov with solar system comets, for which more information is available. Spacecraft missions to comets like 67P/Churyumov-Gerasimenko have measured porosity directly by landing on the surface and analyzing the mechanical properties. These measurements confirm that cometary nuclei are highly porous, with porosities ranging from 70 to 80% in the cases that have been measured. Borisov's inferred porosity is higher, pushing into a regime where few solar system analogues exist. This could mean that Borisov is genuinely more porous than typical solar system comets, or it could mean that the thermal modeling overestimates the porosity due to simplifying assumptions. The question remains open. The observations are consistent with extreme porosity. The models predict extreme porosity, but certainty requires direct measurement, and direct measurement requires proximity. Borisov is gone, accelerating back into interstellar space, carrying its fragile, mostly empty structure with it. 2I/Borisov formed around another star. This much is certain: the hyperbolic trajectory, the excess velocity relative to the Sun, the direction of arrival, all point to an origin outside the solar system. But which star? When did formation occur? What were the conditions in that distant protoplanetary disk? The answers are hidden in the object's properties, its composition, its structure, its isotopic ratios. Each of these carries information about the environment of formation, but the information is incomplete, ambiguous, difficult to interpret. The composition tells something about temperature and pressure in the disk. The structure tells something about the accretion process. The isotopic ratios tell something about the chemical history of the material from which the comet formed, but none of these uniquely identifies the parent star or the formation epoch. Researchers have traced Borisov's trajectory backward through the galaxy, calculating where the object might have been millions of years ago. The trajectory is uncertain because small perturbations from passing stars accumulate over time, making the path increasingly uncertain the farther back the calculation goes. Within the uncertainties, Borisov's past trajectory passes through regions of space near several stellar systems, any of which could potentially be the birthplace. But proximity in the past does not prove origin. The comet could have been ejected from a system elsewhere and passed through these regions by chance. The velocity of Borisov relative to the local standard of rest, the average velocity of stars in the solar neighborhood, provides another clue. The velocity is not exceptionally high, suggesting that the object was ejected from a planetary system with dynamics similar to our own, rather than from a system in a different part of the galaxy with a different velocity distribution. This narrows the possibilities slightly, but not enough to identify a specific star. Only needed one gravitational kick billions of years ago. Only required that planets formed around a star, that their orbits became unstable, that one planet scattered a comet into an escape trajectory. Only took dynamics repeated around countless stars throughout the galaxy. The formation of Borisov's high porosity structure implies gentle conditions during accretion. In the outer regions of protoplanetary disks, where temperatures are cold enough for volatile ices to condense, dust and ice grains drift through a tenuous gas, colliding occasionally at low velocities. Each collision allows the grains to stick together, building larger aggregates over time. If the collision velocities are too high, the grains bounce or shatter rather than sticking. The porosity of the final structure depends on these collision velocities. Gentle collisions preserve porosity. While energetic collisions compact the material, the collision velocities in protoplanetary disks are determined by the turbulence of the gas. In quiescent regions, turbulence is weak and collision velocities are low, perhaps meters per second or less. In turbulent regions, driven by instabilities or magnetic fields, collision velocities can be much higher. Borisov's high porosity suggests formation in a quiescent region, or in a disk with low turbulence overall. This is consistent with models of planet formation that predict gentle accretion in the outer disk, but it is not unique to any particular stellar environment. One mystery is the time scale of formation. Did Borisov form early, during the first million years of the protoplanetary disk's existence, when gas was still abundant and temperatures were relatively warm, or did it form late, after the gas had dissipated and the disk had cooled? Early formation would expose the comet to more intense radiation from the young star, potentially altering its chemistry. Late formation would allow more pristine material to be incorporated, preserving the original chemical composition of the molecular cloud from which the star formed. The composition of Borisov provides some hints. The abundance of carbon monoxide relative to water is higher than the average for solar system comets, but not extraordinarily so. This suggests formation at temperatures where both water and CO ices were stable, perhaps in a region analogous to the Kuiper belt or the scattered disk in our solar system. The presence of complex organic molecules, inferred from the reddish color, suggests that the material underwent some processing, possibly by ultraviolet radiation or cosmic rays, either during formation or during the subsequent journey through interstellar space. Isotopic ratios, if they could be measured precisely, would provide powerful constraints. The ratio of deuterium to hydrogen in water depends on the temperature and chemistry of the environment where the water formed. High deuterium ratios indicate formation at low temperatures, where deuterium-enriched ices condense preferentially. Low ratios indicate higher temperatures or chemical exchange with hydrogen-rich gas. Measurements of Borisov's deuterium ratio are difficult because the emission lines are faint, but preliminary results suggest values within the range of solar system comets, implying similar formation conditions. The oxygen isotope ratios, the relative abundances of oxygen-16, oxygen-17, and oxygen-18, also carry information about formation history. In the solar system, different bodies have different oxygen isotope signatures depending on where they formed and how much mixing occurred in the protoplanetary disk. If Borisov's oxygen isotopes could be measured, they would reveal whether its formation involves similar or different processes. But oxygen isotope measurements in comets are extremely difficult, requiring high-resolution spectroscopy and careful modeling of molecular emission lines. The ejection of Borisov from its birth system likely occurred during the late stages of planet formation, when the orbits of giant planets became unstable or when close encounters between planets scattered smaller bodies into eccentric orbits. This process, known as dynamical instability, is thought to be common in planetary systems. Simulations show that a significant fraction of small bodies formed in the outer disk are ejected into interstellar space during this phase, becoming the population of interstellar objects now drifting through the galaxy. The ejection process preserves the structure of the object if the encounter is distant enough. A close gravitational encounter with a planet generates tidal forces that can disrupt weakly bound structures. But a distant encounter, a gravitational slingshot occurring at several planetary radii, imparts velocity without significant tidal stress. Borisov's intact high porosity structure suggests that its ejection was gentle, a slow acceleration over an extended period rather than a sudden, violent encounter. One hypothesis is that Borisov was ejected from a system with multiple giant planets, where the planets' mutual perturbations created a chaotic orbital environment. In such systems, small bodies can be scattered onto hyperbolic orbits with relatively modest velocity changes, allowing fragile objects to escape intact. This scenario is consistent with what is known about planetary system architectures from exoplanet surveys, which show that many systems have multiple giant planets with orbits that may be unstable over long time scales. Another hypothesis is that Borisov formed in the outer regions of a disk that extended far from the star, perhaps tens or hundreds of astronomical units, and was ejected by perturbations from a distant stellar companion or a passing star. In this scenario, the ejection is even gentler, and the high porosity is preserved more easily. But the frequency of such wide disks and distant companions is uncertain, making it difficult to assess how common this mechanism might be. The age of Borisov is unknown. It could be young, ejected recently from a planetary system that is still dynamically active, or it could be old, ejected billions of years ago from a system that has long since stabilized. The cosmic ray processing of its surface provides a rough lower limit on the age, millions of years at least, but the upper limit is unconstrained. The object could be as old as the galaxy itself, a relic from an early generation of planetary systems. The star that gave birth to Borisov might still exist, quietly burning in some distant part of the galaxy, or it might have evolved off the main sequence, swelling into a red giant or exploding as a supernova, erasing all trace of the planetary system that once orbited it. There is no way to know. The comet carries no record of its parent star's fate, only the chemistry and structure imprinted during formation. The outgassing curve, the plot of gas production rate versus time, reveals the thermal lag most clearly. For a comet with no thermal lag, the curve would peak at perihelion and decline symmetrically afterward. For Borisov, the curve peaks after perihelion, and the decline is slower than the rise. This asymmetry is the signature of subsurface heating and delayed sublimation. Observatories around the world track Borisov's brightness in multiple wavelengths. Optical telescopes measure reflected sunlight, which depends on the amount of dust in the coma. Ultraviolet telescopes detect emission from molecules like hydroxyl, OH, a photodissociation product of water. Radio telescopes observe carbon monoxide and other molecules directly, measuring their abundance through rotational emission lines. Each wavelength provides a different view of the comet's activity, and together they build a comprehensive picture of the outgassing process. The water production rate is estimated from hydroxyl emission. Water molecules sublimate from the nucleus, travel into the coma, and are broken apart by solar ultraviolet radiation, producing OH radicals. The OH emits at specific ultraviolet wavelengths, and the brightness of this emission is proportional to the water production rate. Observations show that water production increases steadily as Borisov approaches the Sun, reaches a maximum around perihelion, and declines gradually afterward. The peak production rate is around 10 kilograms per second, modest by cometry standards, consistent with a small, weakly active nucleus, only needed sunlight to split water molecules apart, only required ultraviolet photons energetic enough to break chemical bonds, only took patience to measure the faint glow and calculate how much water must be sublimating. Carbon monoxide production is measured directly by radio telescopes like ALMA, which detect the rotational emission lines of CO molecules. These observations are more precise than the hydroxyl measurements because CO emits in the radio rather than the ultraviolet, and radio observations are less affected by sky background and atmospheric absorption. The CO production curve shows a clear thermal lag. The peak occurs about 2 weeks after perihelion, and the decline is extended over several weeks. The peak production rate is around 1 kilogram per second, roughly 10% of the water production rate. The difference in timing between water and CO peaks provides direct evidence for depth stratification. Water ice, more abundant and less volatile. Sublimates primarily from the near-surface layers. Carbon monoxide ice, more volatile and possibly concentrated deeper. Sublimates from layers that heat up later and stay warm longer. The 2-week delay corresponds to the time required for heat to diffuse from the surface to the depth where CO ice is stored, consistent with thermal models that place CO ice tens of centimeters below the surface. Dust production is inferred from optical brightness measurements and from the structure of the dust tail. Dust particles are ejected from the nucleus along with gas, and their motion is determined by radiation pressure from sunlight. Larger grains are less affected by radiation pressure and fall back toward the nucleus. Smaller grains are pushed away, forming the tail. By modeling the tail structure and comparing it to observations, researchers estimate the size distribution and production rate of dust. Borisov's dust production is lower than its gas production, giving it a low dust-to-gas ratio, consistent with high porosity that allows gas to escape easily while trapping dust. One subtlety in the outgassing curve is that it depends on the observing geometry. The brightness observed from Earth depends not only on the gas production rate, but also on the comet's distance from Earth, the viewing angle, and the orientation of the nucleus. Correcting for these geometric effects requires careful modeling, and uncertainties in the nucleus shape and rotation state introduce additional errors. Despite these challenges, the thermal lag is robust. It appears in multiple independent measurements, in different wavelength ranges, using different observational techniques. The thermal models used to interpret the outgassing curves solve the heat diffusion equation numerically, accounting for sublimation, gas flow, and the rotation of the nucleus. The models include parameters for thermal conductivity, porosity, ice composition, dust content, and nucleus size. By adjusting these parameters, researchers find the combination that best matches the observed brightness and gas production curves. The best fit models consistently require high porosity, confirming the interpretation that Borisov's interior is mostly void. One mystery that emerges from the models is the depth of the active layer. How deep does heat penetrate? How much of the nucleus contributes to outgassing? The answers depend on the thermal diffusivity and the time available. For Borisov, with several months of exposure to sunlight and high porosity, slowing heat diffusion, the active layer is estimated to extend tens of centimeters below the surface. This is a significant fraction of the nucleus radius if the nucleus is only a few hundred meters across, meaning that a substantial volume of the comet participates in the outgassing, but much of the nucleus remains dormant. The deep interior, beyond the reach of the thermal wave, stays frozen at the temperature of interstellar space. This cold core contains ice that has not sublimated in millions of years, possibly billions, preserving the original composition without alteration. If a spacecraft could sample this material, It would provide a direct window into the chemistry of another star's protoplanetary disk, uncontaminated by solar heating or cosmic ray processing. The asymmetry in the outgassing curve, the slower decline compared to the rise, reflects the thermal inertia of the subsurface. As Borisov moves away from the Sun, the surface cools quickly, but the subsurface retains warmth. This stored heat continues to drive sublimation, maintaining gas production even as the solar heating decreases. The timescale for cooling is similar to the timescale for heating, both governed by the same thermal diffusivity. The comet takes weeks to heat up as it approaches the Sun, and it takes weeks to cool down as it departs. Observations continue into early 2020, tracking Borisov as it moves beyond 3 astronomical units from the Sun. The brightness fades, the coma shrinks, the gas production rate drops below detection limits. By February, the comet is too faint for most ground-based telescopes. By March, even the largest instruments struggle to detect it. The final observations capture the tail end of the thermal lag, the last slow decline as the subsurface finally cools and outgassing ceases. One irony is that the thermal lag extends the observing window, but it also means that the most interesting phase, the peak activity, occurs when the comet is already receding from the Sun and becoming more difficult to observe. If the peak had occurred at perihelion, as it would in a comet with no thermal lag, observations would have been easier, the signal stronger, the data more complete. Instead, observers must track a fading target, pushing their instruments to the limit to capture the delayed response. The outgassing curve also provides constraints on the nucleus rotation. If the nucleus rotates rapidly, heat is distributed more evenly across the surface, reducing local temperature extremes but not affecting the average temperature much. If the rotation is slow, or if the nucleus has a preferred orientation, certain regions receive more heating than others, creating asymmetries in the gas production. Observations of Borisov show modest variations in brightness on timescales of hours, suggesting a rotation period of around 7 hours, typical for small comets. This rotation averages out the solar heating over each rotation cycle, and the thermal lag is determined by the average heating rather than by instantaneous peaks. The models predict that outgassing should continue, at very low levels, for months after perihelion as the subsurface slowly cools. By the time the comet reaches 5 astronomical units, the gas production rate has dropped to levels too low to detect with current instruments, but the physics suggests that trace amounts of sublimation continue. The thermal memory of the Sun persists, fading gradually until the entire nucleus returns to equilibrium with the cold of interstellar space. One question that arises is whether the thermal lag changes the orbital evolution of the comet. Outgassing creates a small rocket effect. The escaping gas carries momentum, and the reaction pushes the nucleus in the opposite direction. This non-gravitational force can alter the trajectory slightly, affecting the time of perihelion passage or the outbound velocity. For Borisov, the outgassing is modest, and the non-gravitational effects are small, but they are measurable. The delayed outgassing due to thermal lag shifts the timing of the rocket effect, potentially creating a different perturbation than would occur without the lag. Researchers calculate the non-gravitational forces by measuring the deviation of Borisov's observed position from the predicted position based on gravity alone. The deviations are small, a few arc-seconds over several months, but they are statistically significant. The magnitude and direction of the non-gravitational force are consistent with a comet producing gas at the observed rate, with the thermal lag slightly shifting the timing of the effect. The perturbation does not significantly change the hyperbolic excess velocity. Borisov is still leaving the solar system on essentially the same trajectory, but it does provide an independent check on the outgassing models. The thermal lag also affects the distribution of gas and dust around the nucleus. In a comet with instantaneous thermal response, The coma is symmetric, expanding outward from the nucleus at the local gas velocity. In a comet with thermal lag, the coma production continues even as the comet moves away from the Sun, creating a coma that lags behind the nucleus in some sense, extended along the trajectory. This effect is subtle and difficult to observe, but high-resolution images of Borisov's coma show slight asymmetries that might be attributable to delayed outgassing. The data from Borisov's outgassing curve are now archived, available for future analysis as models improve and new theoretical insights emerge. The observations are finite. The comet passed through once and will not return, but the information they contain is still being extracted. Each new paper on Borisov reanalyzes the same brightness measurements, the same spectroscopic data, finding new patterns, testing new hypotheses, refining the understanding of this one object that happened to pass through at a time when humans were watching. The journey through interstellar space is long and cold. 2I/Borisov, after its ejection from whatever planetary system gave it birth, drifted through the galaxy for an unknown period, millions of years, possibly tens of millions, perhaps longer. During this time, the comet received no warmth from any star. The ambient temperature of interstellar space is only a few Kelvin, set by the cosmic microwave background radiation left over from the Big Bang. At this temperature, all volatile ices are stable. Water ice does not sublimate. Carbon monoxide ice does not sublimate. Even the most volatile ices, like nitrogen or methane, remain frozen. But the journey is not entirely quiescent. Cosmic rays, high-energy particles accelerated by supernovae, pulsars, and other violent astrophysical processes pervade the galaxy. These particles strike the surface of the comet continuously, penetrating microns to millimeters deep, depositing energy, breaking chemical bonds, creating new molecules from the fragments of old ones. Over millions of years, this cosmic ray processing alters the surface chemistry, darkening the ice, reddening it, building up a layer of complex organic molecules. The surface also experiences impacts from interstellar dust grains. These grains, mostly submicron in size, collide with the comet at relative velocities of tens of kilometers per second. Each impact vaporizes a tiny amount of material, eroding the surface atom by atom. The cumulative effect over millions of years removes perhaps a millimeter of material, creating a slightly processed outer layer while leaving the deep interior pristine. Only needed time and isolation to preserve the interior, only required that no catastrophic event disrupted the structure, only took the galaxy's slow rotation to carry the comet through different regions of space, each with slightly different densities of gas and dust, each contributing to the gradual evolution of the surface. For a high-porosity object like Borisov, the interstellar journey poses a unique challenge. The fragile structure must withstand micrometeorite impacts without collapsing. Each impact sends a shock wave through the porous matrix, potentially breaking bonds between ice grains. But the porosity also provides protection. The voids absorb impact energy through compression, dissipating the shock before it can propagate far. The result is localized damage near each impact site, but the overall structure remains intact. Another challenge is thermal cycling. Though in interstellar space, this is minimal. Without a nearby star, there is no day-night cycle, no seasonal variation. The temperature is nearly constant, varying only slightly as the comet passes through regions of space with different densities of starlight or infrared radiation from dust clouds. These variations are too small to drive sublimation or create thermal stress, so the structure remains stable. One mystery is whether the comet rotates during its interstellar journey. Rotation could be induced by the ejection event, or by subsequent gravitational encounters, or by outgassing during previous passages near stars. A rotating comet experiences no net torque in the emptiness of interstellar space. There is no atmosphere to provide drag, no magnetic field to couple to. The rotation rate, whatever it was at ejection, should remain constant over the journey. Observations of Borisov during its passage through the solar system suggest a rotation period of several hours. But whether this rotation was present throughout the interstellar journey or was induced by tidal torques during the Sun encounter is unknown. The trajectory of Borisov through the galaxy is nearly straight on the scale of millions of years. Gravitational perturbations from distant stars are weak, producing only slight deflections over the journey. The comet passes through the spiral arms of the galaxy, regions of higher stellar density and more active star formation, and through the interarm regions, where stars are sparse. Each region has a different environment, different radiation fields, different densities of gas and dust, different populations of high-velocity stars, but none of these differences are large enough to significantly alter the comet's trajectory or structure. The survival of Borisov's high-porosity structure through the interstellar journey suggests that such structures are robust on million-year timescales, at least in the relatively benign environment of the galactic disk. This has implications for the population of interstellar objects. If fragile comets can survive the journey intact, then the population should include a significant fraction of high-porosity bodies, similar to those found in the solar system's own comet populations. The detection of Borisov, with its familiar cometary behavior, supports this expectation. One hypothesis is that most interstellar objects are comets, icy bodies ejected during planet formation, simply because planet formation produces many more comets than rocky bodies. In the solar system, the Kuiper Belt and Oort cloud contain trillions of comets, far outnumbering the rocky asteroids. If other planetary systems are similar, the majority of ejected bodies should be comets, and the interstellar population should be dominated by icy objects. The detection of Oumuamua, which appears rocky or at least non-icy, suggests that the population is more diverse than this simple picture implies. But Borisov fits the comet-dominated scenario well. Another hypothesis is that comets are overrepresented in detections because they brighten as they approach the Sun, making them easier to discover than non-outgassing rocky objects. A dark, rocky interstellar object could pass through the inner solar system unnoticed, too faint to trigger detection algorithms. A comet, by contrast, develops a coma that increases its effective size and brightness, making it more likely to be spotted. This observational bias could skew the detected population toward comets, even if the true population is more balanced between icy and rocky bodies. The longevity of Borisov's structure also raises questions about the age distribution of interstellar objects. Are they mostly young, recently ejected from still active planetary systems, or are they mostly old, relics from systems that formed billions of years ago and have long since stabilized? Young objects might retain more pristine composition, while old objects might show more cosmic ray processing. Borisov's surface shows evidence of processing, the reddish color, the organic rich chemistry, consistent with an old object, but the evidence is not conclusive. A young object exposed to intense radiation near its parent star before ejection could show similar processing. One small irony is that Borisov survives millions of years in the harsh environment of interstellar space, only to begin disintegrating as soon as it enters the relatively hospitable inner solar system. The Sun's warmth, which seems gentle compared to the cold of space, is what drives the outgassing that slowly erodes the nucleus. Each passage near a star costs the comet a fraction of its mass, and, after enough passages, nothing would remain. But Borisov makes only one passage through our solar system, and it will not return. The mass lost during this single encounter is small, perhaps a few % of the total, leaving the comet nearly intact as it exits. The interstellar journey ends when Borisov enters the Sun's gravitational sphere of influence, at a distance of roughly 1 light-year. At this distance, the Sun's gravity becomes comparable to the tidal forces from nearby stars, and the comet's trajectory begins to curve, bending toward the Sun. The journey inward takes months, accelerating as the distance decreases, until the comet sweeps through perihelion and begins the outward journey that will carry it back into interstellar space. The next star encounter, if there is one, lies millions of years in the future. Borisov will drift through the galaxy, cooling back to the ambient temperature of space, its subsurface finally releasing the last traces of the Sun's warmth. The structure will remain fragile and mostly empty, a survivor of one planetary system's formation carrying the memory of a brief encounter with another. The exit measurements begin in early 2020 as 2I/Borisov moves beyond 3 astronomical units from the Sun. The comet is fading now, the coma shrinking, the brightness declining in a slow exponential decay. Observers squeeze the last data from the dwindling signal, tracking the comet as it moves into the outer solar system, past the orbit of Jupiter, toward the vast, empty region beyond Neptune where the solar system fades into interstellar space. The thermal lag is still visible in these late observations. The brightness does not drop off sharply, as it would if outgassing ceased immediately. Instead, it declines gradually, stretched out over weeks. As the subsurface cools and the gas production rate decreases, the decline is slower than the rise that occurred during the approach to perihelion, confirming the asymmetry predicted by thermal models. The subsurface, insulated by its high porosity, releases heat more slowly than it absorbed it, creating a longer tail to the brightness curve. Spectroscopic observations become increasingly difficult as the comet fades. The emission lines weaken, the signal-to-noise ratio drops, integration times stretch into hours, but enough data are collected to track the gas production rates into February and March, showing that both water and carbon monoxide production continue at low levels even as the comet recedes. The ratio of CO to water remains elevated, suggesting that CO continues to sublimate from the warming subsurface while water production, driven primarily by surface heating, declines more rapidly. Only needed telescopes to stare at the same fading point of light, hour after hour, accumulating photons. Only required that the sky stay clear, that the instruments stay stable, that the comet remain within the field of view, only took patience to extract meaning from noise. By late March, Borisov is beyond 4 astronomical units, and most ground-based telescopes can no longer detect it. The Hubble Space Telescope makes one final observation in April, capturing a faint image of the coma against the background stars. The comet is magnitude 24 now, barely distinguishable from the thousands of distant galaxies that populate the same region of sky. This is the last observation. After this, Borisov fades beyond the reach of human instruments, continuing its journey into invisibility. The final measurements provide closure to the thermal lag story, the brightness curve. From discovery in August through the final detection in April, spans more than 8 months, long enough to capture the full cycle of heating, peak outgassing, and cooling. The data are incomplete, gaps where weather prevented observations, periods where the comet was too close to the Sun for safe observation. Uncertainties introduced by changing observing geometry, but enough information remains to constrain the thermal models and confirm the high porosity of the interior. One mystery that persists is whether Borisov continues to outgas beyond the reach of detection. The thermal models predict that some sublimation should continue until the comet reaches 5 or 6 astronomical units, where the subsurface finally cools below the sublimation temperature of even the most volatile ices. But at these distances, the gas production rate is too low to create a detectable coma, and there is no way to observe the continued activity. The comet might still be slowly releasing gas, invisible, adding a trace of water vapor and carbon monoxide to the sparse medium of the outer solar system. The trajectory continues outward, accelerating as the Sun's gravity weakens. Borisov crosses Neptune's orbit in mid-2020, moving at roughly 30 kilometers per second relative to the Sun. At this speed, it takes years to reach the heliopause, the boundary where the solar wind meets the interstellar medium, and decades to reach the distance of the Oort cloud. But the comet will keep moving, gradually fading into the background population of interstellar objects that drift through the galaxy. The orbital elements calculated from the observations provide a precise description of the trajectory. The eccentricity is 3.36, well above the minimum value of 1, 0 that defines a hyperbolic orbit. The perihelion distance is 2.01 astronomical units. The inclination, the angle between the comet's orbital plane and the plane of the solar system, is 44 degrees, indicating that Borisov approached from well out of the ecliptic plane. These elements allow researchers to calculate where Borisov will be at any time in the future, though the calculations become less certain as the distance increases and small perturbations from distant gravitational sources accumulate. One calculation traces the trajectory forward, projecting where Borisov will be in thousands or millions of years. The comet will pass within a few light years of several stars, but none of the encounters will be close enough to significantly alter the trajectory or capture the comet into orbit. Borisov is too fast, too energetic, to be captured by any single star's gravity without an improbably close encounter. It will continue drifting through the galaxy, visiting no system. Bound to no star, a permanent wanderer. Another calculation estimates how long it will take for Borisov to cool back to the equilibrium temperature of interstellar space. The thermal models suggest that the subsurface retains warmth for months, possibly years. After the Sun encounter, at 5 astronomical units, the surface has cooled to near equilibrium, but tens of centimeters down. The temperature is still elevated, slowly diffusing outward. By the time Borisov reaches 10 astronomical units, even the subsurface should have cooled, and the entire nucleus returns to the uniform cold that characterized it before the encounter. The mass lost during the perihelion passage is estimated from the gas production rates. Integrating the water and CO production over the active period gives a total mass loss of several million kilograms, a large number in absolute terms, but small compared to the estimated total mass of the nucleus. If the nucleus is a few hundred meters across and has a bulk density of 0.05 grams per cubic centimeter, the total mass is roughly a billion kilograms. Losing a few million kilograms represents a fraction of a percent, negligible compared to the nucleus size. Borisov exits the solar system nearly as massive as it entered. One irony is that the exit is better documented than the approach. By the time Borisov was discovered in August, it was already approaching perihelion, and observers had only a few months to prepare. But the exit is expected, and telescopes are already pointed at the comet, tracking its slow fade. The data collected during the exit provide the clearest view of the thermal lag, the delayed cooling, the gradual cessation of outgassing. The exit tells the story that the approach could only hint at. The thermal lag measurements also provide a baseline for future interstellar objects. If another comet-like visitor is detected, observers will know to look for the delayed brightness peak, to extend observations beyond perihelion, to track the slow decline that signals subsurface warming. The techniques developed for Borisov, the thermal models, the spectroscopic analysis, the gas production rate calculations, will be refined and applied to the next visitor, building a comparative data set that reveals the diversity of comets across the galaxy. The final data point is archived in early April 2020. After this, Borisov becomes a historical object, no longer observable, but preserved in the measurements collected during its brief time within reach. The brightness curve, the spectra, the images, all are stored in databases, available for future researchers to analyze, reanalyze, mine for new insights. The comet itself continues its journey, indifferent to whether humans are watching. The thermal lag of 2I/Borisov tells a story about comets, about formation, about the processes that build planetary systems. It is a small detail, a subtle asymmetry in a brightness curve, but the implications reach across the galaxy. The delayed outgassing reveals that at least some interstellar comets have high porosity interiors, structures dominated by empty space, held together by weak bonds between ice grains. This is not exotic, it is familiar. It matches what is known about solar system comets from decades of observation and from spacecraft missions that have visited comet nuclei directly. The familiarity suggests universality. If comets around other stars form through the same processes that formed comets in our solar system, then the physics of planet formation might be universal, at least in its broad outlines. The details vary. Different stars have different masses, different luminosities, different protoplanetary disks, but the fundamental processes, grain coagulation, ice condensation, gravitational accumulation, appear to work the same way, producing similar outcomes. High porosity comets exist here, and they exist out there, drifting through the galaxy, occasionally passing close enough to a star to warm up and reveal their structure. The thermal lag also constrains formation conditions. High porosity requires gentle accretion in low-density environments. If collisions were too energetic, the structure would compact. If turbulence were too strong, grains would shatter rather than stick. The existence of Borisov's porous interior implies that its formation environment was quiescent enough, gentle enough to allow fragile structures to grow without disruption. This places constraints on the properties of the protoplanetary disk where Borisov formed: the gas density, the turbulence level, the temperature profile. Only needed conditions calm enough for ice grains to touch and stay touching. Only required that gravity gathered them slowly, without compression, without violence. Only took time for the structure to grow, layer by patient layer, until it reached the size where gravitational interactions with planets could send it into exile. One implication is that planetary systems with high porosity comets are likely systems where planet formation proceeded gently in the outer regions. Violent systems, those with massive planets migrating inward. Those with close encounters and collisions might disrupt fragile structures, leaving behind only denser, more robust bodies. The presence of Borisov suggests that at least some planetary systems have stable outer regions where fragile comets can form and survive until ejection. Another implication is that the interstellar population of comets is large. If Borisov is representative, and 2 detections within 2 years suggest that interstellar objects are not rare, then the galaxy contains trillions upon trillions of such bodies. Drifting between stars, each one a frozen relic of some planetary system's formation. Most will never approach another star closely enough to warm up. Most will spend their entire existence in the cold of interstellar space, dormant, invisible, carrying their fragile structures through the galaxy until the end of time. The thermal lag provides a window into this population. Without the lag, Borisov would have been just another faint comet, briefly bright, quickly fading, offering limited information about its interior. With the lag, the observations reveal structure, depth stratification, thermal properties, details that allow researchers to infer how the comet formed, how it evolved, what it tells about conditions around other stars. The lag transforms a simple brightness measurement into a probe of cometary interiors, a diagnostic tool that works across interstellar distances. One mystery is how representative Borisov is. Is it typical of interstellar comets, Or is it unusual? The high porosity could be common, a natural result of gentle accretion in most protoplanetary disks, or it could be rare, a special outcome that requires specific conditions. With only one well-studied interstellar comet, the question cannot be answered. Oumuamua provides a counterexample, an interstellar object that does not look like a comet. But whether Oumuamua is rare or common is equally unknown. Future detections will clarify the situation. As survey telescopes improve, more interstellar objects will be discovered. Some will be comets like Borisov. Some will be rocky like Oumuamua. Some might be intermediate or entirely different. Each detection adds another data point, another constraint on the properties of the interstellar population. Over time, a statistical picture will emerge: the fraction of comets versus rocky bodies, the distribution of sizes and compositions, the range of porosities and thermal properties. The thermal lag also has implications for the habitability of planetary systems. High-porosity comets are fragile, easily disrupted by impacts or tidal forces. In a planetary system with many such comets, collisions between comets and planets might deliver water and organic molecules. But the impacts would be low energy because the comets are weak and porous. This could make comet impacts less catastrophic for planetary surfaces, potentially preserving habitable conditions even in systems where cometary bombardment is common. On the other hand, the thermal lag implies that comets can remain active longer during close approaches to stars. Extended outgassing creates extended comas and tails, which could deposit material over a wider region of space. Planets orbiting in the habitable zone might accumulate more cometary material if the comets passing through have high porosity and strong thermal lags, increasing the delivery of volatiles and organics. One hypothesis is that the thermal lag affects the long-term evolution of cometary orbits in planetary systems. Outgassing creates non-gravitational forces that alter trajectories. For comets with strong thermal lags, the non-gravitational forces are delayed relative to perihelion, changing the direction and magnitude of the orbital perturbations. Over many orbits, these perturbations accumulate, potentially moving comets into different orbital regions or even ejecting them from the system. Borisov's thermal lag, though observed during only one passage, provides a template for understanding how these effects work in other systems. The comparison with solar system comets remains important. Spacecraft missions to comets like 67P Tempel 1 and Wild 2 have revealed that these objects have high porosity, though perhaps not as high as Borisov's. The porosity ranges from 50 to 80%, somewhat lower than the 90 to 95% inferred for Borisov. Whether Borisov is exceptionally porous or whether the difference reflects uncertainties in the thermal modeling is unclear. Future missions to solar system comets might find examples with porosities as high as Borisov's, confirming that such structures exist locally as well as in interstellar space. The thermal lag of Borisov has become a case study in cometary science, cited in papers on thermal modeling, porosity, outgassing dynamics, and the interstellar population. It demonstrates that detailed information can be extracted from relatively simple observations, brightness measurements, and spectroscopy. When combined with careful modeling, it shows that the behavior of comets, even those from other stars, is predictable, governed by the same physics that operates in our own solar system, and it hints at something larger, that the processes of planet formation, the outcomes of those processes, the bodies that result, all of these are not unique to our corner of the galaxy. They are universal, or nearly so, repeated around countless stars, producing populations of comets and asteroids and planets that share common properties even as they differ in detail. Borisov is one messenger from this larger population, carrying news that the galaxy is filled with comets much like our own. The invisible population stretches across the galaxy, a vast swarm of interstellar objects drifting through the space between stars. Most are small, dark, cold, too faint to detect except during close approaches to stars, and even then, only a fraction pass close enough and bright enough to be noticed. For every interstellar object detected, thousands pass through the solar system unobserved, moving too slowly to trigger automated surveys or too far from the sun to develop the brightness that would make them visible. Astronomers calculate the population size from the detection rate. 2 interstellar objects confirmed in a few years, combined with estimates of survey completeness and detection efficiency, imply that the inner solar system receives perhaps 1 interstellar visitor per year larger than 100 meters across. Smaller objects are more numerous. The size distribution likely follows a power law, with 10 times as many objects at half the size. Scaling downward, the flux of interstellar objects smaller than 10 meters might be thousands per year, though none of these would be detectable with current technology. Extrapolating to the entire galaxy, the numbers become staggering. If every star produces and ejects comets during planet formation, and if the average planetary system ejects 1 trillion comets, a conservative estimate based on solar system analogs, then the Milky Way contains something like 100 billion trillion comets drifting in interstellar space. Most are in the galactic disk, where stars are concentrated, but some are in the halo. Ejected with high velocities during violent dynamical events, the density of interstellar comets is low, perhaps 1 per cubic light-year in the disk, but the volume of the galaxy is so vast that the total population is enormous. Only needed billions of planetary systems forming over billions of years. Only required that each system scattered a fraction of its small bodies into interstellar space. Only took time for the population to build up. Accumulating ejected comets from every generation of planet formation. Most of these objects will never be detected. They move through the galaxy on trajectories that never approach closely to any star. A comet drifting through interstellar space at 30 kilometers per second takes 30,000 years to travel 1 light-year, and the typical distance between stars is several light-years. An interstellar comet might drift for millions of years without coming within 1 astronomical unit of any star, remaining frozen, dormant, invisible. Even when an interstellar object does approach a star, detection is not guaranteed. The object must pass within the inner regions of the planetary system, where survey telescopes are watching, and it must be large enough and reflective enough to scatter detectable amounts of light. Comet-like objects have an advantage. Outgassing increases their brightness, but non-outgassing rocky objects like Oumuamua are much harder to find. The detection bias favors comets, meaning the true population might include a higher fraction of rocky bodies than the detected population suggests. The velocity distribution of the interstellar population reflects the velocity distribution of stars in the galaxy. Stars orbit the galactic center with velocities of around 200 kilometers per second, but their velocities relative to each other are much smaller, tens of kilometers per second. Set by the random motions of stars within the disk, interstellar objects ejected from planetary systems inherit the velocities of their parent stars, plus the ejection velocity from the planetary encounter. The result is a population with a broad velocity distribution, most moving at tens of kilometers per second relative to the Sun, but with tails extending to much higher and lower velocities. Borisov's velocity, about 30 kilometers per second relative to the Sun, is typical of this distribution. It is fast enough to be clearly interstellar, but not so fast as to suggest an exotic origin. The velocity is consistent with ejection from a planetary system in the galactic disk, with no evidence for a high-velocity kick from a close encounter with a massive object or a gravitational slingshot from a stellar binary. One implication of the large population is that interstellar panspermia, the transfer of life between planetary systems via interstellar objects, might be feasible, at least in principle. If some fraction of interstellar comets carry microbial life frozen into their ice, and if some fraction of those comets impact planets in other systems, then life could spread through the galaxy on timescales of hundreds of millions of years. The hypothesis is speculative, and the probabilities are uncertain, but the sheer number of interstellar objects increases the chances that such transfers could occur. Another implication is that planetary systems are not isolated. They exchange material continuously, ejecting comets into interstellar space and capturing comets from elsewhere. The solar system has likely captured interstellar comets over its history, and some of the objects in the Oort cloud might be interstellar in origin, captured during the Sun's early encounters with nearby stars in its birth cluster. These captured objects would be difficult to distinguish from native comets without detailed compositional analysis, but they represent a form of cross-contamination between planetary systems. The detection of interstellar objects is improving as survey technology advances. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2020s, will survey the sky every few nights with unprecedented sensitivity, detecting faint, fast-moving objects that current surveys miss. Simulations suggest that Rubin Observatory will detect several interstellar objects per year, building a statistical sample that will allow researchers to characterize the population's properties, the size distribution, the composition distribution, the velocity distribution. One goal is to detect an interstellar object early enough to mount a spacecraft mission. Both Oumuamua and Borisov were discovered too late for any realistic mission to intercept them. By the time mission planning could begin, the objects were already leaving the solar system, moving too fast for any existing spacecraft to catch. But if an interstellar object is detected on approach, months or years before perihelion, a rapid response mission might be possible. Such a mission would provide close-up images, compositional analysis, and direct measurements of properties like mass, density, and internal structure, information that cannot be obtained from telescopic observations. The thermal lag observed in Borisov provides a target observable for future missions. A spacecraft flying by an interstellar comet could measure surface temperature with infrared sensors, probe subsurface structure with radar, and sample outgassing composition with mass spectrometers. The combination of thermal measurements and gas analysis would directly test the porosity models, confirming or refuting the high porosity interpretation and revealing details about the internal structure that thermal modeling can only infer. One small irony is that the interstellar population, though vast, remains mostly invisible, known primarily through inference and statistics rather than direct observation. The two confirmed detections are outliers, exceptional in that they happen to pass close enough and bright enough to be noticed. The rest of the population remains hidden, drifting unseen through the dark between stars, a cosmic ocean of small bodies that outnumber the stars themselves but remain beyond the reach of telescopes. The thermal lag of Borisov, in this context, is a rare glimpse into the properties of this population. It is one data point, one measurement, one object among trillions, but it is a beginning, a proof of concept that interstellar objects can be studied in detail, that their internal properties can be inferred from observations, that the physics governing them is accessible to human understanding. Each future detection will add another data point, gradually filling in the picture of what drifts through the galaxy, unseen, in the space between worlds. The comet is beyond 5 astronomical units now, moving outward through the empty space where planets are sparse and sunlight is weak. The outgassing has ceased. The coma has dissipated. What remains is a dark, frozen nucleus. A few hundred meters of ice and dust and void, cooling back toward the temperature of interstellar space. The subsurface still holds traces of warmth, the thermal memory of perihelion. But even this is fading now, diffusing outward through the porous matrix, radiating away into the vacuum. The trajectory continues, unchanging. 30 kilometers per second, directed away from the Sun, toward a region of the galaxy where no planets orbit, no telescopes watch, no instruments wait. The comet is returning to the state it held for millions of years before the encounter: cold, dark, dormant. The brief activation, the months of outgassing, the thermal lag that revealed so much, all of this is ending, settling back into the stillness that characterizes most of the comet's existence. There is no sound in space. No wind moves across the surface. No atmosphere carries vibration. The comet travels in silence, a silence so complete that it seems to extend not just around the object, but through it, through the frozen grains and the empty voids, through the structure that survived so much to arrive here and will survive so much more as it departs. The stars shift slowly, changing position as the comet's motion carries it through the galaxy. Constellations that were familiar from Earth's perspective rearrange themselves. Stars that seemed close separating. Stars that seemed distant drawing nearer. But these changes are gradual, imperceptible on human timescales. For the comet, traveling at 30 kilometers per second, it will take thousands of years for the stellar background to change noticeably. Tens of thousands of years to move 1 light year. Millions of years to approach another star. The warmth continues to leave. Deep in the interior, tens of centimeters below the surface, the temperature drops degree by degree, approaching the ambient cold of interstellar space. The process is slow, governed by the same thermal diffusivity that created the lag during heating. Heat diffuses outward through the porous ice, radiates from the surface as infrared photons, dissipates into the surrounding vacuum. By the time the comet reaches 10 astronomical units, the temperature profile will be nearly flat again. The entire nucleus in equilibrium with the cosmic background radiation. No observers watch this cooling. The comet is too faint now, too far, too small against the vastness of space. The telescopes have turned to other targets, tracking asteroids, monitoring stars, searching for the next visitor. The data collected during Borisov's passage are archived, preserved, but the comet itself has passed from observation into memory. The structure remains intact. The high porosity that defined the comet's thermal response, the fragile lattice of ice grains with vast voids between them, continues unchanged. The sun's warmth removed only a small fraction of the mass, a few percent, eroding the surface but leaving the interior largely untouched. What drifts outward now is nearly the same object that drifted inward months ago, carrying the same structure, the same composition, the same story of formation around another star. Time passes differently for objects in space. There are no seasons, no days, no markers to segment the flow of time. The comet simply exists, moving, cooling, silent. Years become decades, become centuries. And the motion continues, uninterrupted, undisturbed. The galaxy rotates beneath it, stars forming and dying, planetary systems emerging and evolving. But the comet remains unchanged, a frozen snapshot of conditions from long ago. Perhaps it will approach another star, millions of years from now. Perhaps it will warm again, outgas again, reveal its structure to observers around a distant sun. Perhaps it will be captured by a planetary system, settling into an orbit, becoming a periodic comet rather than an interstellar wanderer. Or perhaps it will continue drifting, forever, through the dark between stars, never warming again, never observed again, carrying its thermal memory of our sun into a future so distant that the sun itself will have changed beyond recognition. The thermal lag fades into the past. The delayed outgassing, the slow cooling, the subsurface warmth that persisted for weeks after perihelion, all of this becomes history, a sequence of events that happened once and will not repeat during this comet's journey through our solar system. The lag was a moment, brief on cosmic scales, when the comet's interior was not in equilibrium, when warmth from the sun penetrated deep enough to tell a story about structure, about porosity, about how ice and void combine to create objects that can cross the galaxy intact. Now equilibrium returns. The temperature approaches uniformity. The comet settles back into the state that characterizes most of its existence: frozen, dormant, patient. There is no urgency in interstellar space, no schedule to keep, no destination to reach. The comet moves because it is moving, continues because there is nothing to stop it, exists because it has always existed and will continue existing until some future event, collision, capture, tidal disruption, ends its journey. The galaxy is full of such objects, most unseen, most unknowable, drifting between stars on trajectories set millions or billions of years ago. They are the debris of planet formation, the scattered remnants of processes that build worlds. Each one carries information about where it came from, encoded in composition and structure and motion. Each one is a messenger, though most messages are never read, never received, never even noticed. Borisov was noticed. For a few months, it was visible, trackable, measurable. The thermal lag it displayed told something about comets in general, about structures that can form in protoplanetary disks and survive ejection and drift intact through interstellar space. It confirmed that physics is universal, that comets around other stars resemble comets around our own, that the space between worlds is filled with objects that would be familiar if only they could be seen. Now it fades back into invisibility, back into the population of objects too far and too faint to detect. The instruments lose signal, the observations end. The comet continues, unobserved but still existing, still moving, still carrying its structure of ice and void through the slow galactic rotation. Somewhere, perhaps, another comet is beginning its own journey toward the sun, still too distant to detect but approaching, warming, preparing to reveal its own story. The cycle continues. The galaxy produces these travelers constantly, scattering them through the disk, populating the space between stars with frozen fragments of planetary history, and in the cold, in the dark, in the silence between stars. 2I/Borisov travels onward, cooling slowly, carrying the last traces of our sun's warmth into the deep night of interstellar space, where time moves slowly and nothing disturbs the stillness, and where comets drift forever through the dark, patient, cold, and quiet. The thermal memory fades, the warmth disperses, the comet cools, and still it travels. Still.